Hello. Yes, we welcome you back to PSSB, Physical Sciences Silver Bullet. And it's me, Richard. Okay, we are having this question, which comes from vertical projection. The statement reads, consider the velocity time graph below of a ball. Okay, this is the graph we are looking at. And then the question comes, what does each of the following represent? So we are having all these ones as indicated on the graph. What do they represent? Okay, let's start with 5.88 meters per second. What does it represent? Okay, let us actually describe the entire journey. Okay, we are having a ball. They said it's a ball which is projected here. The ball is projected upwards and it moves, it reaches maximum height in 0.6 meters. Then from maximum height, it turns and starts to move downwards. It hits the ground at the velocity of 19.6 meters per second. After hitting the ground, it bounces. And on bouncing, it bounces and goes until it reaches maximum height. Then, after reaching maximum height, it turns down and comes down and hit the ground. So the entire journey took 3.2 seconds. So now let us now describe what each one represents. What does 5.88 meters represent? It represents the velocity at which the ball was projected. Okay. Then minus 19.6 meters per second. What does it represent? It represents the velocity at which the ball strikes the ground. Okay. Then we come to the time of 0.6, this one. So what does it represent? It represents the time taken for the ball to reach maximum height from point of projection. Then 2.6 seconds, what does it represent? 2.6 seconds represent the time taken for the ball to move from point of projection to the time when it strikes the ground. So the entire journey from point of projection going to maximum height, then from maximum height to come down and strike the ground, that entire journey took 2.6 seconds. Then 3.2 seconds, what does it represent? It represents the time taken for the ball to move from point of projection until it strikes the ground, then bounces upwards, reaches maximum height, then comes down to the ground. That entire journey took 3.2 seconds. Let me repeat. The ball moved from point of projection, went to maximum height, came down, struck the ground, then bounced, went to maximum height, then came down and struck the ground again. That entire journey took 3.2 seconds. So that is that. So let's look at the next question. Yeah, then comes the question 10.2. It says calculate the height above the ground from which the ball was dropped. Okay, when you look at the graph, what is that height they are talking about? Okay, let's look at the motion of the ball. The ball was projected upwards. It reached maximum height. Then from maximum height, the ball turned the direction and moved downwards until it struck the ground. So I have a lot of data here. So a lot of it actually. Let us look at here. We have the initial velocity, which is 5.88 meters per second. I have the final velocity at which the ball strikes the ground as negative 19.6 meters per second. Negative comes up as a result of choosing upward as positive. I have G, the ball was initially projected upward, so it's going to be negative 9.8 meters per second squared. I have the time, so the data is simply too much. The entire journey took 2.6 seconds. So what am I looking for? They want the displacement. So we have more than one equation to use. We can use the third equation. We can use the second equation. Both of them are applicable. So if we use the second equation, which says Vf squared is equal to Vi squared plus 2a delta x. On substitution, what do we have? We are having minus 19.6 squared. Initial velocity is 5.88 squared. And what do we have? 2 times negative 9.8 delta x. So when you look at that equation, the only unknown is 1, which is delta x. So we rearrange and then get the answer from the calculator. Let us see what we can get. Okay. Yeah, this is what we get after substitution. It is minus 17.84. Minus comes about because the displacement you are calculating is below point of projection. So remember that when displacement is below point of projection, it's minus. And when it's above point of projection, it is positive. So that is that. It is 17.84. That's the maximum, that's the height above which the ball was dropped. So we got the next question. Okay. Then comes this question. The time at point P indicated on the graph. This is our point P. Okay. Now, this is a very interesting scenario if you follow it very closely. Okay, let's repeat. The ball was projected upwards. it reaches maximum height after 0.6 seconds, then moves downwards and hit the ground. So I want you to realize that this is the point when the ball hits the ground. This is the point when the ball bounces off the ground. So let us indicate it here in terms of positioning. I'm going to start from here. I'm going to start at the point when the ball is projected, is bouncing upwards, going, reaches maximum height, and it comes back to strike the ground again. This point I'm talking about is where we find time 2.6. And this point I'm talking about here is where we find the time 3.2. Okay. So, and our point P lies here. So that is the sketch of the positioning of the ball. Now you have to remember that for a ball which is projected upwards, reaches maximum height, then comes from maximum height and comes back to the point of projection. This is the truth about it. About when it comes to time, the time taken to reach maximum height, which is delta t, is equal to the time taken to move from maximum height back to the point of projection. That is true. So if that is true, what can we say? This is what we say. What we say is that if you get the difference in this time, which is 3.2 minus 2.6, that difference is going to be equal to 2 delta t. We want to find this time range. So what do we get from there? So the difference here, we got it as 0.6. So the entire range here in terms of time is 0.6. But 0.6 is made up of 2 delta t. So what are you going to get here? We can get delta t, which is equal to 0.6 over 2, giving you 0.3 seconds. Okay, after getting 0.3 seconds, what does that mean? They want time at P. Now you have to recall that what we have just got is the range. What's the range? From this point to P is 0.3. And from P to this point is 0.3. And time is cumulative. What do we do with our 0.3? If you add 2.6 to 0.3, you'll get time at T, at P. So what are you going to say? Time at P is given by 2.6 plus 0.3, giving you what? 2.9 seconds. The reason why I normally write seconds in full is to not confuse 5 with S. So it's 2.9 seconds. So that point is 2.9 seconds. Then comes this question. It says, calculate the maximum height reached after first bounce. Okay. So what do we have here for this part? This is what we have. Let us look at the information. First of all, you have to remember that first bounce means this. Remember, the ball hit here and bounced here. So this is the bounce. The ball moves from that point up to here. So this is our bounce. A to B is our bounce. It bounced until it reached maximum height, and that's what they want here. So what information do we have there? First of all, this is what we know. We know the time range. You have just calculated it from here up to here. We found that it is 0.3. So that's the time taken to reach maximum height. Okay, what else do we know? We know the velocity at maximum height. That happens to be our final velocity. And what is it? 0 meters per second. What else do we know? We know G, the ball is moving upwards. So it's going to be negative 9.8 meters per second squared. Then we bring in our unknown. What is it? Maximum height. So that's the information we have. When you look at that information, what equation is that one? Now there's a problem. Here we have our final velocity. And the equation we know, it has initial velocity. So this is what you have to know. Okay. The ball moved and moved like that. In other words, it bounced, reached maximum height, then came down. And you have to remember that this time interval, we found it as 0.3 seconds, and the same applies to this one. Okay. So, which means that these two sides are similar. This half is similar to that half. So, because the equation we have requires us to have initial velocity, because we are going to use the third equation, we are going to use this half. And what do we get from this half? Sorry. What do we get from this half? This is what we get. Remember, now we are taking this one as x and y. That's the side we are going to take. Okay. So if that's what you are taking, we have our initial velocity in this case as 0 meters per second. Okay. We know our time, which is 0.3 seconds. We know our g is going downwards, which is going to be 9.8 meters per second squared. And we are looking for delta x. Yeah, that trick works so that we don't have to struggle very much. I repeat, we didn't have VI here. Because the equation we are going to apply is this one. What's the equation? It says delta x is equal to VI delta t plus half a delta t squared. So with this, what do we do? We substitute. This is what we get after substitution. So our delta x is going to be equal to, so after substitution, we get our maximum height reached after first bounce as 0.441 meters. Okay. So with that, we are going to cut this video here. We thank you for your time. I will truly appreciate it. The channel is PSSB, Physical Sciences, Silver Bullet, and me, Richard. See you another time. Bye-bye.